Okay, today we're going to talk about limiting reactants. I don't know if we'll get to percent yields or not, but we will finish that up tomorrow. Tomorrow I had scheduled just a work day, so if we need to go over just a little bit, we can. Yeah, so we might have 10, maybe 15 minutes left of notes to take tomorrow. You'll be able to do most of it except for 3 questions. There's going to be 3 questions that you can't do. So limiting reactants are talking about in a reaction you have 2 reactants and one of them is going to get used up first and it's going to limit how much product you can produce. So that's why it's called limiting. The other reactant is called excess because you have extra of that left over. So if we use our the students in the desk in this room as our reactants and then the product would be a student in the desk, in our room, what is the limiting reactant? Which one gets used up first, the students or the desks? So you run out of desks first before you run out of students, right, before you get all the desks filled, so there's extra desk empty. Well, in our class right now. If I had 25 enrolled, then what? Then the desks are limiting, right? So it's the same idea, except we're going to use chemicals in our balanced equation. We're going to know how much of each reactant we start with, and then you're going to have to choose one and calculate how much are you actually going to use up of the other reactant, and compare that to how much you have, and see whether or not you have enough. So we aren't really adding any more steps to our conversions. We're just going to do a step at the end of comparing some numbers. So this is a very simplified problem. This is a balanced equation, all 1-to-1 ratio. So if I have 5 moles of carbon and 10 moles of oxygen, to react all 5 moles of carbon, how much oxygen do I need? If it's a 1-to-1 ratio, I have 5 moles of carbon. If I want to figure out how many moles of oxygen do I need? It would just be 5. So I need 5 moles of O2. And a lot of times I put needed when I do this calculation here. So I remember that's how much I need. In order to react all 5 moles of carbon, I need 5 moles of oxygen. I have 10 moles. Do I have enough? Do I have enough oxygen? If I need 5 and I have 10. Yes. So the limiting would then be carbon, because oxygen is excess. That automatically makes the second reactant the limiting. If I would have done the calculation in the other direction, so I would have started with 10 moles of O2, how many moles of carbon would I need? 10. And I only have 5, so do I have enough now? No. So either way, carbon is my limiting reactant, just showing that it doesn't matter which number you start with. You're still going to get carbon as the limiting reactant, oxygen is the excess. We were going to use up 5 moles of oxygen, so we have 5 moles excess, 5 moles extra, and the limiting is the carbon. Because when we calculated, we said we need 5 moles of oxygen in order to react all the carbon. Right? That was that calculation. We started with 5 moles of carbon and calculated how much oxygen. So we have extra because we have 10 moles sitting here to be used, and we're going to use up 5. So that makes this oxygen excess, which if this is an excess, that makes this limiting. Does that make sense? Let's try one more, see if it helps. It's going to be the same thing, but a little different. We'll have a little more complicated equation. Silicon dioxide is usually quite unreactive, but it will react readily with hydrogen fluoride. It's hydrofluoric acid. According to this equation, is it balanced? Are you sure? It is. If 2 moles of hydrofluoric acid are exposed to 4.5 moles of silicon dioxide. What's the limiting reactant? So you can choose either one. Do you want to start with 2 or 4.5? It doesn't matter. Colton, what's going on over there?
His phone just went off and it was like
Do we want to start with 2 or 4.5? 2. Okay. So we're going to start with 2.0 moles of HF. Nope, doesn't matter. We are going to convert into moles of our other reactant. Since both numbers are given to us in moles, we want to compare the same units, so we need it in moles. We're going to have one next that they're in grams, so we're going to convert to grams instead. Depends on what the numbers they give you. So how do I convert moles of HF into moles of SiO2? The coefficient. So I have 4 moles of HF on the bottom. Oops, that's F, not E. And 1 mole of the SiO2 on top. Yes. So that gives us 1/2, 0.5 moles of SiO2 needed. Okay, so this is how much I'm going to have of SiO2 in order to react all of this hydrofluoric acid. How much do I actually have? I have 4.5 moles. Do I have enough? Yes, because I have 4.5, I'm going to use up 0.5. So which one's limiting? No, you just told me I have extra of that. So HF has to be limiting. That's excess. How much excess do we have? 4 moles excess, yep. So let's just show that if we would have started with 4.5 moles instead, so let's say we would have chosen to start with 4.5 moles of the SiO2. We would have 4 moles of HF on top this time and 1 mole of SiO2 on bottom. And we'd have gotten, what is that, 18? Because we have SiO2, we started with 4.5 moles of SiO2. So moles of SiO2 have to go on bottom. And the 4 is just from the coefficient. Right. We don't want to put 4 moles of HF on the bottom, otherwise our units won't cancel. So if we would have started with 4.5, we would have said we need 18 moles of HF. How much do we actually have of HF? 2. We only have 2, so do we have enough? No. So either way, HF is going to be limiting. Okay, last problem on this one, and we'll talk a little bit about percent yield. The black oxide of iron, Fe3O4, occurs in nature as the mineral magnetite. This substance can also be made in the laboratory by the reaction between red-hot iron and steam according to the following equation. 3 Fe plus 4 waters. Is it balanced? 4, 8, oxygen. Yep, it would be. So the question says, when 36.0 grams of water is mixed with 167 grams of iron, what's the limiting reactant? So we're going to convert, we get to pick a number. Which number do you want to start with? Doesn't matter. 36. We're going to convert 36 grams of water into grams of iron to see how much iron is needed to react all of this water. So 36.0 grams of water. To convert, we need to change this to moles first. So how do we do that? Uh-huh. Find the molar mass. Mm-hmm. 18.02 grams. On bottom or top? Yep. From the coefficient, and on top would be So then we're going to convert moles of iron back into grams since this number is in grams. 55.85. Oops. So to do that calculation, I think you get 50 or 85 something. Or 83. Yeah. 83.68 grams of iron. Okay, this is how much is needed. So now look at how much we have. Whatever you calculate is the amount that would be needed to react all of this water. Anything the part that you calculate.
So you did 167 first, and that would be needed?
Then whatever you calculate for water would be the needed part, yep. Right, because we need 83.68 grams. We have 167 grams. So we have plenty. So H2O would be limiting. Now we're going to skip to C because it just will be easier since I'm going to erase all the numbers. It says what mass in grams of excess reactant. So which one is the excess reactant? Iron, because the water is limiting. That makes iron is excess. How much remains when the reaction is complete? So how much is left over? How do you do that? Subtract it. Mm-hmm. Good. And then B, what mass in grams of black iron oxide, so this part right here, Fe3O4, is produced? Do we want to start with the 36 or 167 for this? This time it does matter. Do we react all of the 167? No. So which one's limiting the amount of product produced? The water. So we want to start with your limiting reactant because that's what's limiting the amount. So we want to start with 36 grams of water and convert that into grams of the iron oxide. So we already said that was 18.02 grams. And that was 4. And this time we're going to go to Fe3O4. So I want to find the molar mass of that for me. 231. Oops, I put the Fe3O4. So how much is produced? You can't do that in your head? No, that's too much. 36 times 231.55 divided by 18.02 and then divide by 4. No, I have 115.65. You took 36 times 231.55 and then divide by 18.02 and then divide by 4? Or did you multiply by 4? Make sure you divide. So the important part is that you use the limiting reactant to find how much product you produce. And once you calculate, this is how much should be produced. This is called the theoretical yield. That's the theoretical yield. How much theoretically, if you actually did this reaction in lab, how much you should get. Now we'll find, and we'll talk about tomorrow, that reactions are not 100% efficient. So usually you will not get that much. You will usually get less than that. So what you will use is, it's called percent yield, to show how efficient that reaction is. When you actually do the reaction, you're going to use how much you actually produce and the theoretical yield to find the percent yield. But that's where we're going to stop today, and then tomorrow we'll talk about percent yield.